Yeah. So this is lecture number 4. We are going to do the sandwich theorem for the sequences. Pretty much easy actually. The statement you already know, but let's say how it works, right? So what I want to say is, so let an, bn and cn are three real sequences such that En is less than equal to Cn, Cn is further less than equal to Bn, right? And limit n tends to infinity, En exists is equal to L, limit n tends to infinity, Bn also exists is equal to L. So what I want to claim at the sandwich sequence between these two, that is Cn, that will also converge and will converge to the same limit. That means then, yes. So we'll prove that fact. Okay. Otherwise, I don't think so proof is that much necessary, but just in order to, make you feel like that, okay, you are convinced that how it works, right? So let's start the proof. So now, given that En and Bn are convergent to L, right? So if they are convergent to L, so what would I say? I would say that by definition, I would say that for every epsilon positive, however small, doesn't matter, right? The challenge is, the challenge can be any number, which is no matter how much small it is. So for every epsilon positive, however small, there exists a number m1 such that En minus L can be made less than epsilon for all n after that cutoff, that is what? M1, right? So most of you know the definition, right? That how we have made this definition, okay? Are you comfortable with this definition?
Yes, sir.
Right? Because n is convergent. That's what we have done in the first lecture, okay?
Yes, sir.
So similar definition will be also applied to Bn. So what would I say? For every epsilon positive, however small, there exists a number. Now this defender may be different, right? Because the sequence is different, okay? M2 such that Bn minus L is less than epsilon for all n greater than equal to M2. Now I'll explain that part, that why these defenders are different. Okay, so let me give you a simple example. Let you take the sequence to be 1 by n, you take the sequence to be 1 by 2n. So there are two sequences. Suppose you take the two sequences of that, right? So now if you take 1 by n and both are converging to 0, right? But you give same challenge to them. Let's say you want it to be less than 1 by 10. So here n should be greater than what? 11. And what about this one? Here n should be greater than what?
n by 2.
5.
Yeah, 5. That means that's it. Is it okay?
Yes, sir.
Yes, sir.
So what you are saying, that there are two different sequences converging to the same limit 0, having the same challenge, but it may have different defenders. Is it okay?
Yes, sir.
Right?
Yes,
But suppose I want to make this happen after every n. So what should I say? So this is the sequence who actually start working just after 5, but it is a little bit slower, the first one, and this inequality will start satisfying after n is greater than 11. So suppose I want to find out the common place where both these inequality will get satisfied. So what is that common place? Tell me.
6.
No. After 6, it will not start satisfying, right?
N greater
11.
than
Will be
11.
n greater than 11.
Yes. So how you make the choice? How
The
do you?
greatest of the two.
Yes, exactly. So if we want to, satisfy both of these inequalities simultaneously, so what we do, we actually take the maximum of first and second. Is it fine?
So why 11? Why not 10?
See, at 10 it will not work, no? Because 1 by 10 is not less than 1 by 10. Yeah, I mean equal to 11. Yeah, you are right in saying
Yes,
this.
sir.
Yeah. So I would say 10. Okay. More precisely, I would say 10. Right? Is it fine?
Yes, sir.
Is it fine now? Is it fine with everyone?
Yes,
Yes,
sir.
sir.
Yes, sir.
So I'm clearing that page. So now I'll now therefore choose maximum of M1 and M2. Now we actually do not know what is this maximum of M1 and M2. Now M1 may be the maximum or M2 may be the maximum. We really don't know about M1 and M2, right? So whatever the maximum is, we actually change its notation and we say that it is M. So if it is say 11 and if it is say 6, then it will come out to be 11. And if it is says this is 6, this is 11, then M2 would be the maximum, right? So we do not know about the maximum of M1 and M2. So we just keep a new notation for the maximum. We say that the maximum will be notated by M, right? So now if it is maximum notated by M, then both these conditions will hold simultaneously. That means for epsilon greater than 0, however small, an minus L would be less than epsilon for all n greater than equal to m or greater than simply greater than m, and bn minus L is also less than epsilon for all n greater than m. Is it okay? Is it right?
Yes, sir.
Sir, so basically we are taking the intersection among the M1 and M2 we have.
We are taking the intersection of the part where actually both are satisfying.
Okay, sir.
Right? Otherwise, we are taking the bigger cutoff.
Yes, sir.
Because we know that, see, one sequence is satisfied after 6, another is satisfied after 11, right? One inequality is satisfied after 6, another is after 11. So as you say, the intersection starts from 11 onwards, right?
Yes, sir.
Okay, so is it fine now?
Yes, sir. Yes, sir.
Yes, sir.
Okay.
Yes, sir.
From this inequality, can I write it as minus epsilon to an minus L to plus epsilon for
Yes, sir.
all n greater
Yes,
than
sir.
Yes, sir.
Yes, sir.
And
Yes, sir.
similarly, I can write it as L minus epsilon to an to L
And
plus
yes, sir.
for all n greater than n,
Yes, sir.
right? But the same thing is happening for Bn as well, right? Same thing is happening for Bn as well. Okay?
So why minus epsilon?
Because the modulus property, if mod x is less than a, that means x lies between minus a and a.
Okay, sir.
So now you know that your an is less than equal to cn and your cn is less than equal to bn and your bn is also less than L plus epsilon and your an is also less than L minus epsilon,
Yes, sir.
right?
Yes, sir.
For
Yes,
all
sir.
n greater than n.
Yes,
True?
sir.
Yes,
Yes,
sir.
Yes,
sir.
sir.
So that means what? So I can write it as, so let's say I don't need this an and bn right now. So let's discard these two. So can I write the inequality as L minus epsilon to Cn L plus epsilon for all n greater than m? Can I
Yes, sir.
write this?
Yes, sir.
I can simply drop these terms, right? Because this will
Yes,
also hold.
sir.
So I can simply go to the modulus form again. Can I write as this form?
Yes.
Yes.
So what does that mean? So you started with for any epsilon positive, and now you say that there is a cutoff n so that it will happen, right? So that actually means what? That means Cn is convergent to L. Is it okay?
Yes, sir.
Yes,
Is
sir.
it fine?
Yes, sir.
Okay. So we'll do a few questions on that. So let's say now, let's say the sequences show that limit n tends to infinity cos n by n is equal to 0, right? So now you know that we know that cos n lying between
Minus 0 and 1.
-1 and 1,
-1 and 1.
Sorry, yeah, sorry.
right? Right? True?
Yes, sir.
Yes, sir.
So can I write it in this way that cos n, can I write in this way that cos n lying between -1 by n to cos n by n lying between -1 by 1? किसी के माइक में प्रॉब्लम है, can you please switch it off? So cos n by n lies between -1 by n to 1 by n.
Yes, sir.
Okay, so now you see this, now you compare it. This is your an, this is your bn, okay, this is your bn, and this is your cn. Now if you take limit n tends to infinity an, that means limit n tends to infinity -1 by n, this will come out to be 0. And if you take limit n tends to infinity bn, that means limit n tends to infinity 1 by n, which is again 0. So by sandwich theorem, cos n by n limit n tends to infinity as it is cn, it will also be 0.
0.
Is it okay?
Yes, sir.
Yes, sir.
Yes, sir.
So there are few rules which probably, some of the rules which you already know. So let me remind you. Okay. So let an and bn be two sequences such that limit n tends to infinity an is a some number and limit n tends to infinity bn is some number b, right? So there are few rules which you maybe already know. Some rule, sum and difference rule.
Yes, sir. A plus B and A minus B.
Right, yeah. So limit n tends to infinity. If you take the addition of these two sequences, then the answer will be a plus b. And of course, if you take the subtraction, then the subtraction will also hold. Second was the product rule. So limit n tends to infinity, an times the bn will be a times the b. So it doesn't matter if you take some constant number over there,
It's going to
right?
be
Let's say,
multiplied.
yes, k times the bn, so it will come out to be k times the
AB.
b, right?
Yes.
And the last one is the quotient rule, that limit n tends to infinity, an upon bn will be equal to a by b,
Keeping B
only
cannot be 0.
one exception, that is b should be
B cannot.
non-zero, right? B cannot be 0. So for okay, so there are a few more rules which I should state you, and I'm not doing the proof of that. So if you want the proof, I'll prove those results and I'll post that on my website. That can also I can do that. Okay, so the results will be using those results in our subsequent questions. That's why I'm stating those results. So results are, so the first one is limit n tends to infinity log n by n is equal to 0, right? So few are actually pretty much common. You know that how to prove it. Like for this one, you know that it is infinite by infinite form, right?
Yes, sir. Yes.
You can apply the L'Hopital rule over
Yes,
here.
sir.
So differentiation of log n will be 1 by n,
1 by
and
n.
differentiation of n will be 1.
1.
So limit n tends to infinity, 1 by n would be equal to 0,
0.
right? So these are the rules you can always do. And next, limit n tends to infinity. So I'll give you a few hints. You can do that. So this is n raised to power 1 by n. So how can you do that?
And this to the power.
Sir, 1 to the power infinity.
e to the power.
Yeah, e to the power, that can be done taking log, assuming this to be
Yes,
x
sir.
and then taking log.
Yes, sir,
right?
log like n.
That's how you can do it. So probably you have already done it. I don't know. Maybe in some class you've done it. Okay, so let's say limit n tends to infinity x raised to power 1 by n. This will also 1, considering x to be greater than 0. Right? Fourth one, which we have already done, we know that if you take xn, that would be 0 if your mod x is less than 1. That means a number which is lying between -1 and 1, you'll keep on increasing its power. So what you get, you know that n tends to infinity, xn will come out to be 0. True?
Yes, sir.
Right?
Yes, sir.
Okay. So the fifth one, limit n tends to infinity 1 plus x by n raised to power n, that is e raised to power x. You know its definition, right? And this
Yes,
holds
sir.
for all x belongs to the real. And the last one is limit n tends to infinity xn upon factorial n is equal to 0. It is slightly hard to prove it. I'll post that proof into the classroom. Okay. So let's do a few questions, and then you'll come to know that how the questions needs to be solved. So let's say these are from exercise 8.2. Okay. So let's take few questions. So let's say question number 3. So we want to find out the limit n tends to infinity, whether it does exist or not. That's we're gonna check. So can you see this? Right? Can you
Yes,
see
sir.
this?
Yes,
Okay.
sir.
So
Yes, sir.
you know that. So the basic rule is you
Minus
take
1.
the highest power common, right? So
Yes,
that is 1 by n.
-1.
-2 upon 1 by n plus 2.
Is it okay?
Yes, sir.
So that
-1 upon.
n was taken common, and then so it becomes 0 minus 2 upon 0 plus 2.
0
So that is
minus
minus
1.
1, right?
Yes, sir.
Okay. So let's talk about this one. Question number 11. Okay. So that question is, so limit, we want to evaluate this thing. N plus 1 by 2n, 1 minus 1 by n. So you simply write it as limit n tends to infinity 1 by 2 plus 1 by n, 2n, right?
By 2.
And 1 minus 1 by n. So you know that 1 by 2n and 1 by n will result in 0.
1 by
So
2.
1 should be
1 by
1 by 2. So that is limit n tends to infinity sine pi by 2 plus 1 by n. So how are you going to do it?
Simply by putting the value of n in the
N.
and then we
Yes,
get sine pi by 2. That's 1.
yes,
Yes,
but
sir.
but there is a point which that should be, I mean, that must be told to you. So actually what you're doing, you're taking that limit inside the sine function, right? And then you are putting it. But this may not hold every time. So when it will be true, that I'm gonna discuss the scenario. So we are not going to do the proof of that, but we'll state the result. So that is, there is an important theorem, and that theorem says if An is a sequence of real numbers and converging to L, right? And f of x is a continuous function. F of x, let me write it more precisely. F of x is a function which is continuous at x is equal to L, right? So always keep in mind, so we are adding these two things, that function should be continuous at x is equal to L. So that means that limit, right? Then and defined at all an's, then limit n tends to infinity f of an is also equal to f of L. So in our case, right, in our case, we have a function. See, we want to find out this thing. Right? So sine is a continuous function, na?
Yes, sir.
Okay.
So
That's why we can take
Yes,
it
sir.
inside. In other words, I would more precisely, I would say this, that we can write it as limit n tends to infinity an. That means we can take this limit inside. Okay.
Yes, sir.
So we can take this limit inside the function. Okay. So now, since your sine is a continuous function, so that's why we are able to do this. Every time it may not be true. So now we can write it as sine pi by 2, that is 1. Okay. This is just one result. Just to keep in mind that this may not work every time. Right?
So what is x and L here?
X and L, x is just a function, right? L is the limit of the sequence. Let's say we have a sequence. This is our sequence. The an is pi by 2 plus 1 by n, right? And if you take limit n tends to infinity, so it will become
Pi by 2.
Yeah. So this is your L over here. Okay? And this is your an. Right? And your fx is sin x. Now, can you see the things now?
Yes, sir.
So is it fine?
Yes, sir.
So let's say question number is this 27. That is limit n tends to infinity 1 plus 7 by n raised to power n. So can you do it? Can you give me some suggestions?
E raised to power 7.
Raised to 1.
raised to power
Sir, e ki power 7.
E to the power
Yeah.
7 is the answer.
e की power
Yeah. So how are we gonna do it?
Sir, it's
Fx minus 1 into gx
Property.
e ki power
1 plus x by into property.
Yes, we have done that thing, na?
Yes.
Yeah,
Okay.
that was there, right? So by directly that result, we can write it as e raised to power 7. Okay, so let's say next is question number 35. We want to find out the limit n tends to infinity 4n n n. So how we can do it? Can I do in this way?
Yes,
No.
sir.
Yes. Yes, sir.
No. Right? No or
Yes,
yes?
sir.
No.
Yes,
Sir, where's
sir.
the half
Yes.
also? Half.
Yes, sir.
Yes, sir.
Limit n tends to infinity 4
4,
n raised to power 1 by n. And at that we have already done. This we got
1.
1. So answer will be 4.
4.
Okay? True?
Yes, sir.
So let's move to the next thing. So let's do one more question. That's it. And then we'll be done. Okay, let's finish the lecture over here. Okay, I'll post few more questions that
Thank
will
you,
be in
sir.
the separate video.